All right, so we're gonna good morning. We're gonna start on kinetic energy and thermal expansion. We're gonna continue on with our lesson about heat in materials. So we're gonna start off. So thermal expansion is a result of an increase in kinetic energy of the particles in an object. So as you know, kinetic energy is the energy of motion. So a change in an object's kinetic energy is going to be indicated that a transfer of energy to or from an object is happening. If the kinetic energy of the object increases, then some form of energy is being transferred to the object. If the kinetic energy decreases, then the object is transferring kinetic energy to something else. So have you ever wondered how corn is able to pop into popcorn? It involves a transfer of energy. So when you make popcorn, heat is going to be flowing into the tiny droplets of water inside the kernel, which is going to be causing the liquid water to turn it into vapor. The vapor is going to build up this enormous pressure inside of it, and the kernel is going to explode, turning into the piece of popcorn that we know today. So if you're looking at this image right here, so you're going to be looking at atoms, right? So if the kinetic energy is going to be increasing, then the particles or the atoms are inside an object are going to be vibrating faster. They're going to be colliding more often, and they're going to be expanding. So we're going to have, for example, let's say if this was an ice cube, particles are going to be vibrating faster when the increase in kinetic energy occurs. If there is if you warm it up, for example, you're going to have an increase, and your solid is going to be turning into a gas. I mean, not a gas, a liquid, and thus the liquid is going to be turning into a gas. So we're going to be moving on to this different standard. So in this standard, we're going to be observing and explaining the light that is reflected, refracted, and or absorbed with an object. So if you do have your textbook, we're on page 52 to 60 for the next one. If you don't worry, I do post enough things for you to be able to do the lesson check accurately either way. So if you've ever been to the beach, you've seen how different kinds of waves move. So some ocean waves crash into rocks or piers, while others reach the shore smoothly. Rays of sunlight hit the surface of the water, and some bounce off while others pass through. In general, when waves encounter different medium, they're either reflected, transmitted, or absorbed. Some waves are completely blocked by an obstruction, but their energy is not absorbed or converted to another form of energy. So these types of waves bounce off or reflect from these obstructions. In a reflection, the wave bounces off and heads in a different direction. The law of reflection states the angle of incidence equals the angle of reflection. This means that the angle at which the wave strikes the material will match the angle at which the reflected wave bounces off that material. So shown in our figure. So light reflecting from a mirror is the most familiar types of reflection. The echo voice from the walls of a canyon is another example. So if we're looking at this particular picture, so we have two different angles. So you can tell it's going to be creating this 90-degree angle right here. We have the incidence ray come in, going to be creating this angle of incidence. Then we have the angle of reflection, which is the same angle. It's going to be just called an angle of reflection. So remember, the light that's coming in is the angle of incidence, while the angle that's coming out is the angle of reflection. And this is, for example, a mirror. Refraction, on the other hand, usually occurs in water. So imagine riding a bike down a smooth asphalt road. When you turn off the road into a dirt path, for example, the transition can be jarring. If you might have to grip the handlebars hard to keep the bike going straight, as each wheel is on a different surface. When light waves are transmitted from one medium into another, they also bend in different directions. This bending is due to a refraction, or the bending of waves due to a change in speed. When a wave enters a new medium at an angle other than perpendicular, it's going to be changing direction. For instance, when light is directed at an angle at water at an angle, the light slows down and bends downward. The wave bends towards normal, the imaginary line that runs perpendicular to the boundary between the two media. So if you're looking at, let's say this straw, okay, so if you see the straw is going to be trying to bend where it is supposed to bend. So we see here, we see this straw, right? We see this. So it's pretty much for this one, this image in particular, because these are a little different. This one there, this bottom portion is going to be trying to recreate this 90-degree angle instead of keep going straight. Okay, And that's what refraction pretty much does. It's just bending of these waves because the speed of the let's say the air outside and the speed of water is not going to be the same because of the molecule in it. Did you ever wonder how you can hear someone speaking even if they are around the corner of a building or a doorway? So this is an example of diffraction. So waves don't only travel in straight lines, they are also bend around objects. You can observe diffraction with water waves as well as sound waves. Water waves can diffract around a rock or an island in the ocean because tsunami waves are diffract all the way around an island. People on the shores of the entire island are at risk. So remember, diffraction can be seen right here. So we have a specific source of energy coming in. Now diffraction is going to make sure that it's spreading out all over the place. So like they said, so in a tsunami, so we have a huge wave come in. Now if the huge wave comes into the shore, it's going to spread out all along the land and all the people around it are going to be affected. So absorbent. So when you think of something being absorbed, you might think how a paper towel soaks up water, for example, but waves can also be absorbed by certain materials too. So in absorption, the energy of a wave is transferred to a material it encounters. So when ocean waves reach a shoreline, most of the energy is absorbed by the shore. When light waves encounter the surface of a different medium of a material, the light waves may be reflected, refracted, or absorbed. What happens to the wave depends on the type of materials they hit. Light is mostly absorbed by dark materials, such as the surface of a parking lot, and most reflected by light materials, such as snow. So if we think about clothing, for example, right? If it's really, really sunny outside, you wouldn't want to be wearing a black shirt. It's going to be absorbing all of these incoming heat waves, UV rays, things like that. So it's going to be absorbing all this extra heat that we do not need. In contrast, though, if you wear a white shirt, for example, it's going to be reflecting most of the energy of UV rays that are coming in. It's going to keep you cooler than a black shirt. There is two types of interference. So have you ever seen two ocean waves collide opposite directions to the moment? So they momentarily form a bigger hill-like shape before continuing in their original direction. This is an example of wave interference. There's two types. The first one is constructive interference. So the example of two waves of similar size colliding and forming a wave with an amplitude greater than either of the original wave is called constructive interference. You can think of these waves helping each other, adding their energies together. So as shown in the picture I put, when the crests of two waves overlap, they make a higher crest. If two troughs overlap, they might make a deeper trough. In both cases, the amplitude of the combined crest or trough increases. So if you're looking at our wave, okay, we have wave one, we have wave two. It's going to combine together and make these large waves. So this wave, if we look at our parts of the waves, so we have up here, we have our crest. Crests are a top part, bottom, trough. Okay, amplitude is going to be the measurement if you draw an imaginary line between these straight across. From the middle line, so from the middle portion of our wave to the top, or the middle portion of our wave to the bottom, it's going to be called amplitude. So amplitude is pretty much cutting this wave in half just like this, and it's going to be the measurement of that. So when we look at our crest, both our crest up here, both our crest down here, both of our troughs, they're going to be combined into making this large wave. So our amplitude is going to be increasing. So our amplitude here, for example, is not very high, but when you cut this in half, you're going to see that, for example, from here up, we're passing a lot more space than we are in these original waves. So be constructive inference, you are constructing a new higher wave. Now, destructive interference is when two waves combine to form a wave with a smaller amplitude than the original wave had. This is called destructive interference. Destructive interference occurs when the crest of one wave overlaps the trough of another wave. If the crest has a larger amplitude than the trough of the other wave, the crest wins and part of it remains. If the original trough has a larger amplitude than the crest of the other wave, the result is a trough. And if the crest and the trough have equal amplitudes, they cancel each other out. As shown in the figure that I put, diffraction interference is used in noise canceling headphones, for example, to block out distracting noises in the listener's surroundings. So we have this wave. So if you see the crest up here is going to be matching up with the trough down here. Same thing up here. Our trough matches up with our crest. So if all of these match up and they have the same amplitude like these two waves do, we're going to have a diffraction interference of pretty much this straight line. So if this trough had a higher amplitude than our amplitude down here with this crest, then we would have down here, we would have a slight trough. Same thing over here. If this amplitude on our wave 2 is smaller than our amplitude on wave 1, so if wave 1 had a higher amplitude and our crest was up higher, then you're going to see a small little crest up on our other wave. Standing wave. So look at these ropes. Okay. So the rope is tied at a doorknob and everyone shakes the free end. The motion can generate a standing wave. A standing wave is a wave that appears to stand in one place. Standing waves are produced by two waves interfering with each other as they travel in opposite directions. Standing waves on the rope appear when an incoming wave and a wave reflected from the doorknob have just the right frequency to interfere. So in a standing wave, diffraction interference between two colliding waves produces points of zero amplitude, called nodes. The nodes are always evenly spaced along the wave. Points of maximum amplitude or standing waves are called antinodes. Antinodes always occur halfway between two nodes. The frequency and wavelength of the interfering waves determine how many nodes and antinodes the standing wave will have. When seen in real life, the antinodes appear to pulse in and out of the rope's rest position, while the nodes appear motionless. So standing waves can sometimes appear on lakes when the wind and pressure around them are just right. The water appears to have a node in the center of the lake, and the water waves roll around that node. So remember, this node is just a point of zero amplitude. So it looks like nothing's moving right here. Well, antinode is going to be our highest point right here. Okay, so our antinode is just the opposite of our node. Think about the last time you swung on a swing at a playground. So you might have noticed that it's difficult to get yourself going. Once you're in motion, you can pull on the chains of the swing and jump your legs right time to keep yourself swinging. The swing has a natural frequency, and your actions match the frequency to create greater amplitudes in your motion. So most objects have at least one natural frequency or vibration. Standing waves occur in an object when it vibrates at once of these natural frequencies. When a nearby object vibrates at the same frequency, it can cause resonance. The resonance is an increase in the amplitude of a vibration that occurs when external vibrations match an object's natural frequency. When engineers build a bridge, they have to make sure that bridge supports are not placed at potential nodes for a standing wave. Otherwise, wind could cause the bridge to swing wildly like a rope and collapse. Understanding the resonance of different materials is also useful for people who build guitars, violins, or other wood-based stringing instruments. If the wood in a guitar, such as the one I can put a picture up, resonates too much with a certain note, it may sound too loud when the particular note is strummed. Likewise, if the wood does not resonate with any particular note, the instrument will lack volume or presence and sound dull. So what this is pretty much saying is that resonance, it means that the external vibrations are going to match the object's natural frequency. So you need to make sure, for example, if you are building a wood guitar, that the note is going to be resonating with the guitar, because if it doesn't, then the frequency is going to be off, the noise, the sound is going to be off, and it's just going to sound extremely weird. So we're going to pause here for today. I hope you guys are doing good at home. I hope that we are doing all of our work. Make sure to check the Edmodo every single day for our class, for other classes also, to do the work, because everything is going to be turning into grades. So please make sure you're doing all of your work and have a good rest of your day. Have a good day. Bye.